Today, we are digging deep into a really fascinating paper from DeepSeek-AI. It challenges a core assumption about how we teach large language models to reason. What if, instead of just making them imitate human thinking, we could actually incentivize them to discover even better ways of reasoning, all on their own? Well, that's the central idea behind DeepSeek-R1.
All right, so here's our game plan. We're going to start by really understanding the problem, what the paper calls the reasoning ceiling. Then, we'll dive into their pretty radical R10 experiment. From there, we'll see how that raw power got refined into the final polished R1 model, track its performance along the way, and wrap it all up with the big takeaway, why incentives might just be the key, maybe even more so than imitation.
So right at the start, the paper hones in on this huge bottleneck. The main way we do post-training right now is by showing models these high-quality, human-annotated examples of reasoning. And look, it works, but it also puts a hard cap on the model's potential. Its performance is fundamentally limited by the quality of the examples we can give it. It's learning to copy our homework, not necessarily to solve the problem in a new, maybe even better way.
And that, of course, brings us to the core research question they're trying to answer. Is it actually possible to set up a training environment where a model can break free from the limits of its human training data? Can it evolve its own more advanced reasoning strategies? This is the hypothesis that really drives this whole study.
Okay, so let's really break this down. The standard way of doing things, the conventional pipeline, is supervised fine-tuning, SFT, followed by some reinforcement learning. SFT is all about baking in those human reasoning patterns, but the paper makes a great point. These patterns are often not optimal for a machine. Think about it. Human thought has all these implicit, nonverbal steps, rereading a problem, pausing to think, stuff that just doesn't show up in a written-out solution. For an LLM to learn those things, they have to be made explicit.
So to really put this idea to the test, the researchers did something pretty radical. They created a model they called DeepSeek-R1, and they did it by completely skipping the initial SFT step. Yep, they just took a base model and threw it straight into pure reinforcement learning. The only reward it got was for getting the final answer right. No hints, no guidance on how it should get there.
Now, the tool they used to pull this off was Group Relative Policy Optimization, or GRPO. For anyone deep in the weeds with PPO, the key innovation here is pretty slick. They got rid of the value model. So instead of training a whole separate network just to predict future rewards, GRPO estimates the advantage by simply comparing the reward of one response to the average reward of a group of other responses to the same prompt. This makes the whole process way more computationally efficient and much more stable at a massive scale.
And you can really see why this choice was such a game changer. Looking at the math benchmark, GRPO doesn't just outperform a standard PPO implementation, it nearly ties with a perfectly tuned one. So you're getting similar, sometimes even better performance without the huge cost of training a value model and all that painful hyperparameter tuning. It just made this whole thing practical.
And the results? I mean, they were absolutely staggering. On the AMI 2024 math competition benchmark, R10's accuracy just exploded, going from a baseline of 15.6% all the way up to an incredible 77.9% in just over 10,000 training steps. This wasn't some small incremental gain. This was a fundamental leap in its ability to reason.
But what's maybe even more interesting than the final score is how the model got there. It wasn't just guessing answers correctly, it was developing brand new behaviors. You can see a little piece of its thought process here, where it literally stops and says, wait. That's an aha moment. This is huge. The model learned on its own to pause, to question its own logic, and to backtrack. It's a textbook example of emergent reasoning. Okay, but R1-0 wasn't perfect. You could almost think of it as this kind of raw, untamed genius. Its reasoning was powerful, sure, but the outputs were a mess, often unreadable, sometimes mixing English and Chinese in the same thought process. Plus, it was so focused on reasoning that it lacked general conversational skills. And that brings us to the next phase. How do you engineer that raw power into the final, polished DeepSeek-R1 model? To solve this, the team built this really clever multi-stage pipeline. They began with what they call a cold start, SFT, on a small, high-quality dataset, just enough to give it a human-aligned conversational style. Then came the really tricky part, a balancing act. They alternated between RL stages to keep pushing its reasoning and SFT stages that mixed in a bunch of non-reasoning data. The whole goal was to make it a more well-rounded model without making it forget all that powerful emergent reasoning it had discovered as R10. And this is absolutely key.
The real magic in these RL stages was the sophistication of the reward signals. They went way beyond just right or wrong answers. They built in model-based rewards for general helpfulness and safety, and they even added a specific reward just to enforce language consistency, directly targeting that language mixing problem from R10. All right, so that's the complex setup. The big question is, did it actually work? Let's track the model's evolution and see how its performance changed at each key point in the pipeline.
And this really tells the whole story, showing the trade-offs and the ultimate wins. You see R10's raw power on the Amy math benchmark, and the pipeline managed to keep that incredible reasoning ability, even nudging it up a bit in the final R1 model. But look at everything else. The Code Forces rating for coding ability just keeps climbing, and the most dramatic change is the Arena Hard score, which measures human preference. It leaps from 53.6 all the way to 92.3. They actually pulled it off. They blended raw reasoning with human alignment.
All right, so after going through all of that, what's the big takeaway from the DeepSeek-R1 story? What should we walk away with?
Well, the paper's conclusion is pretty bold. It basically suggests a paradigm shift. To get to the next level of AI reasoning, maybe we don't need these massive, expensive datasets of human thought. Maybe the key ingredients are simpler. A huge set of really hard problems, a verifier you can trust to check the answer, and enough compute to let the model go to work. It's a fundamental shift from imitation to pure incentivization.
Now, to their credit, the authors are very upfront about the challenges that are still on the table. Pure RL is always going to be vulnerable to reward hacking if your verifier has any flaws. The model also tends to be token inefficient. It can overthink easy problems. And there are still big challenges in areas like software engineering, where the time it takes to evaluate a solution for RL is just too long to be practical right now. And that really leaves us with a provocative thought, a critical question for the entire field. If the new formula for unlocking superhuman performance is just a set of hard problems and a reliable verifier, what new frontiers does that open up? Think about domains like mathematical proofs, drug discovery, or material science, places where verifying a solution is way, way easier than finding one in the first place. This paper suggests we might now have a whole new and much more powerful way to get there.